Hi guys, in this video I'm going to use Google Sheets to do a one-way ANOVA and subsequently a Tukey Kramer multiple comparison procedure using this example here. And we're really going to use Google Sheets as somewhat of a calculator on steroids. It's going to help us with some of the calculations along the way. Okay, so just to be really brief, these values, I have other examples where I talk about these four suppliers. These might be slightly different numbers here, so don't rely on them being equivalent to the previous examples. So this is fresh. We're going to do this one in Google Sheets. So here's my four suppliers, okay, and they happen to be parachute suppliers, and what we've measured from each of them is the tensile strength of the parachute fabric that they supply us. So a higher number here indicates a stronger fabric. So as you see, I have 5 observations from each of the suppliers, making this a balanced design, and there are 4 suppliers. So what I want to do ultimately is to see whether there is any difference among the 4 suppliers with respect to the mean tensile strength of the fabrics that they provide. So here's my data. Okay, so I provide, so I can start first by gathering some information. So first off, let me say that it might be wise to calculate the x bars and the s squareds, the sample means and the sample variances, right under each of the groups instead of creating a new kind of row for each of those. You can organize this however you like. So this is going to make my life a lot easier. I'm going to calculate the average of each of the suppliers. So that's the average, the sample mean, of course, not the population mean, which is what we're after. The sample mean tensile strength. And let's also calculate the sample variance of each of the samples that we've collected. So in Google Sheets, A is going to do that for us. That's sample variance. Okay, so we quickly get these values out of the way, and in fact, let me reduce some of these decimal places. Okay, so just looking at this, glancing at this quickly, we see that supplier 2 seems to have a significantly higher sample mean tensile strength than, say, supplier 1. So we can't say as of now whether that's going to be a significant difference, because this is sample data, and sample data always has the issue of sampling variability inherent in it. So we need to go through with the procedures and rely on our knowledge of probability in order to come to our conclusion. So quickly, our hypothesis is, the null hypothesis is that mu1 equals mu2 equals mu3 equals mu4. So all of the suppliers have the same population mean tensile strength versus the alternative that at least one of these suppliers is different than the others. And let's just use an alpha of 0.05 for this test. Okay, so that's our level of significance. So this is our hypothesis statement. So it would not be a bad idea to jot this down somewhere here. Mu1 equals mu2 and so forth. Okay, so and the alternative, ALOI, that's just an abbreviation of what we know, at least one inequality. So this one-way ANOVA is often referred to as an omnibus test because it tests a lot of things simultaneously, and the merits of that are obvious, but the downside of that is that it doesn't give you the fine detail as to which, if any, of the groups are different than the others. Okay, so we'll get to that. So back to kind of gathering information. We're going to need a grand mean. So x bar bar, so that's an x with 2 bars on top. And that's going to be the average of either all of the X bars or all of the data. And if you do it either way, you'll see you'll get the same value, and that's only because this is a balanced design. Okay, so let's move on. We need the what else should we get in this stage? How many groups do we have? Well, clearly we have 4 groups. How many observations are in each group? I use the symbol N with a little dot at the bottom for that, for my formulas, but it's just my convention. So obviously we have 5. It's a balanced design, so we have 5 in each group, right? N is the total number of observations. Be careful, not N dot. And since there's four groups, 5 in each, that's 20. Okay, and now I think we can get to the formulas for calculating the F-test statistic. So let me leave that there for now. Let me get the components here. I need to get S squared underscore pooled. So that's my way of writing the pooled variance. Okay, without spending too much time on kind of getting the notation perfect. S squared underscore pooled. So what this is pooling the variances. So we're going to pool them by averaging them. Okay, and S squared underscore X bar. This is the variance of the X bars. So here, var A. Okay. And now that we have all these components, we can calculate our F-test statistic. So F is N dot times S squared X bar divided by S squared pooled. Okay? And so we see, let's reduce these decimal places, it's too much. We see that our F-test statistic here is 3.46. Okay, and in order to do anything with this, we need to compare it to something. So we're going to compare it to FU, which is the F upper critical value. So this we can get from a table, and I have my table set up here. So here's my F table, and you see that this F table is for an alpha of 0.05. And we have a numerator degrees of freedom along this count, the row, and denominator degrees of freedom along the column. So if we just quickly go back and see what our degrees of freedoms are, we'll see that degrees of freedom numerator for F, so maybe I should do, is C minus 1, and C minus 1 for us, that is annoying, is going to be 3. F degrees of freedom denominator is N minus C, which is going to be 16. So taking these two guys back to that table that we were just looking at, we see that we have 3 numerator degrees of freedom and 16 denominator degrees of freedom, and if we were to zero in on that, we would see that our F upper critical value, our FU, is 3.24. So let's bring that back. Okay, and now we can make our decision whether we're going to accept or reject our null hypothesis. And here we see, because F is larger than FU, is greater than FU, even though it's not by that much, we will reject HO and conclude that there is at least one inequality among the 4 suppliers with respect to tensile strength. Okay, so not all these suppliers are providing the same tensile strength for parachute fabric. Okay, that's interesting, but what that doesn't tell us is which of these suppliers is different than which of the other suppliers. To do that, there is a follow-up procedure. Sometimes people go directly to this procedure, but I'll do it as a follow-up called the Tukey Kramer procedure. Here I'm going to do the Tukey Kramer procedure because I rejected the null hypothesis in my one-way ANOVA. Okay? So, Tukey Kramer procedure. What we need to do is set up a little table here. This helps a lot. ABS for absolute, diff for difference, and let's do critical range. And you'll need one more column maybe, means different, like a question mark. Okay, so since we have 4 suppliers, we have many pairs to compare. In fact, you can use C times C minus 1 over 2 to be sure that you're comparing the right number of pairs. So since C is 4, we're going to have 4 times 3 over 2, which is 6. So we have 6 pairs we're going to have to compare here. So it doesn't matter which order we do it in. Let's just make sure we do them all. So let's do 1 to 2. That means supplier 1 to supplier 2. 1 to 3. 2 to 3. 2 to 4. And then 3 to 4. I think I've covered them. 1, 2, 3, 4, 5, 6. Yes, I got them all. Okay? Now the next column, we're going to compute the absolute value of the difference in their sample means. So if I'm comparing group 1 to group 2, supplier 1 to supplier 2, I'm going to take the mean from supplier 1, subtract it from the mean from supplier 2, right, because I'm here, and I'm going to take the absolute value of that, which means if it's a negative value, the negative sign disappears, more or less. Okay, so to do that, I can do ABS, and inside the parentheses, I'm going to do this guy minus this guy. Okay, and I'm just going to continue doing this for the right pair. So here 1 to 3. Here 1 to 4. Here 2 to 3. Here 2 to 4. And finally here 3 to 4. Okay? Make sure you're highlighting the correct means. Next, I need the critical range. In order to get the critical range, I must know how to calculate that. The formula for the critical range is a value that comes from the studentized range distribution called a Q upper critical value. So that's a QU. So we're going to get that from a table. Then we're going to multiply that by the square root of the pooled variance, which we calculated earlier. That's a subscript pooled, sorry. Divided by n dot. Okay? So, here's our pooled variance. Here is our n dot. And all we need to get now is this guy from a table. So let's learn how to get that, and then we'll incorporate that all together into this value. Once we get this value, it's just the same value because of the nature of this balanced design. Okay? Okay, so let's go to the table and get QU. So in order to get QU, we need a few things. So maybe I'll put them here. QU, you need alpha, which we have 0.05. You need degrees of freedom numerator, so this is slightly different than the F degrees of freedom. You need degrees of freedom denominator. And how do you get these? Well, for numerator degrees of freedom, it's just C, so C was 4. For denominator degrees of freedom, it's the same as for the F denominator degrees of freedom. n minus c, which was 20 minus 4, so we have 16. So alpha was 0.05. We had this from earlier, right here. Okay, now taking these guys to the table, we're going to be able to get this value here. So here's the Q table. These are the critical values of the studentized range Q table. Okay, so this is for an alpha of 0.05. Let me see if I can zoom in a bit more. Okay, numerator degrees of freedom again are on the first row. So what do we have? 4. And denominator degrees of freedom 16. So it works very much like the F distribution table. The F table rather. So here we get 4.05. Okay, let's take that value back to our spreadsheet here. And if you don't have the same exact tables as me, Google, and you should be able to find both an F table with 5% level of significance and a Q table or studentized range table with the same alpha. Okay, so you can work along with me. If you're using Excel, you can even use a formula to get that. You don't need a table. Okay, so back to where we were. So to get the critical range, remember the formula was QU, and I'm going to lock that. So I hit F4 times the square root of S squared pooled. That doesn't change. I'm going to lock that. F4 key on my keyboard. Notice that puts dollar signs. Divided by N dot. And also I'm gonna lock that. That means make it an absolute reference. You see all my references here are things we just talked about, and I've absolute referenced all of them. Okay, so pause this. If this is new to you, pause it, rewind it, listen to it again, and see what happened in this formula. See what I clicked on and how it matches up with the formula for the critical range that I just gave you. Okay, once you're ready, come back, enter. I get 4.47, and let me reduce these decimals too much. If I pull this down, I will not get the same. I will not get different values. Rather, I get the same value, and that's because I made all these references absolute. That's what those dollar signs are. It's almost like putting concrete on a reference. It does not change no matter where you drag it. Okay, all right, back to here, and final step here in the Tukey Kramer procedure is to compare the absolute difference between a pair and the critical range of that pair. So if the absolute difference is greater than the critical range, then that pair have significantly different means. Okay, so we can just simply eyeball this, and we can say yes or no. And by yes, I mean yes, the means are significantly different between supplier 1 and supplier 2. And you see why I said that, because 4.74 is greater than 4.47. If we quickly scroll down, glance down the rest of these guys, you see that none of the other ones are going to be significantly different. So the answer to the rest of these is no, they are not significantly different. So it turns out that in this particular example, the difference between supplier 1 and supplier 2 was the only significantly different mean tensile strength difference. Okay, all the other pairs, when compared pairwise, meaning one supplier to another, did not exhibit significant difference. Okay, so our conclusion here, if that was not clear enough, is that we rejected the null hypothesis in our one-way ANOVA at an alpha of 0.05. And then we went on to do Tukey Kramer because we rejected our null hypothesis there. And the Tukey Kramer revealed to us that there was only one pair that was significantly different. Okay, interesting. That's not always the case. Sometimes all of these would be different yeses. Sometimes there would be a scattering of yeses and nos. This particular time, there was just one yes. Okay? Alright, so I hope this was helpful. Another example on One-Way ANOVA and how to do it through Google Sheets, be it a little quicker than the previous one. And also an introduction to how to do a Tukey Kramer procedure for a one-way ANOVA, where you've rejected the null hypothesis. Okay? So, till next time, keep watching and have a great day.